Now we are going to talk about when you have multiple images. Say we have a video. So we want to find out how we can analyze the video. Minimum number of frames you need is at least 2. If you have 2 frames, you can compute motion. So it's very important basic operation in the video analysis is what is called optical flow. And so the idea is, given these 2 images, in these images, as you see, there is this car is moving in this direction, and there's this car moving in this direction. So given these 2 images, for every pixel we want to come up with the vector, which we call optical flow. It's a 2-dimensional vector. It gives you a displacement of each of the pixel compared to previous frame, that how much that pixel moved compared to previous frame. So all these pixels, we show the motion, and since this car is moving this way, so we have these vectors showing that how it's moving, and this car is moving other direction, so we have optical flow for that. So that displacement vector is called optical flow vector, and given these 2 images, we want to write a program which automatically computes the optical flow. Every pixel we want to get that vector. So this pair of images is from, it's called Hamburg taxi sequence. This has a historical background, because if you look at the computer vision history, the motion analysis was started by a couple of very famous researchers. One was Hans Nagel from Germany. He was at Hamburg, and then there was Jake Agarwal from UT Austin, and so on. So in old days, it used to be very difficult to get these pictures and videos, because cameras were not that good, and video was very expensive, and so on. So this was the first sequence which Hans Nagel's group recorded and digitized and made it available. So for a long time, this was a standard. If you develop any algorithm, you have to apply it to this one and compare with other methods. So that's what's called Hamburg taxi. Okay, so these are more examples. Now there are lots of video sequences. There's somebody playing table tennis. So for every pixel, we want to have this vector, and this is a method we're going to talk about how to compute this. These are the results from Lucas Canade. There's another sequence playing tennis, and these are the vectors. And this is another famous sequence called the Gordon sequence, where the camera is moving, and due to that it induces a motion, the background on this tree. Again, we are showing the vectors. Now there will be always a problem of the vectors when they are at a boundary. As you see that here there's a problem there. It's very hard to compute the correct vectors at the boundary because there's a discontinuity. So see, there is this tree, there is some motion here, and then this is a background, which is like this. This is a different motion. Okay, so there's a discontinuity, this motion to that motion, so you'll have a problem there. Then within the tree, we'll have more uniform motion. And this, in a way, show you a sequence of the optical flow. We are computing this flow between 2 frames, first and second, second and third, third and fourth, and so on. And we show that as a movie. So here we show the overall motion that people are circling around Kaaba. It is showing you this is the motion mostly. And this is another crowded sequence. So there's a group of people moving this way, another group of people moving that way. So this is another visualization of the optical flow. This is more examples. Another way to show the optical flow besides the vectors is what is called color coding. So here we are showing the color is give you a direction of motion. So if it is red, it's moving in this direction. If it's green, it's moving in this direction, and so on. And the magnitude of the motion or the speed of motion is shown by the the intensity of this color coding. So as you see, visualization is very good that this is moving like that, and there are these two groups of people. Group moving here mostly from right to left, other one moving in other direction. There is this traffic sequence. Again, you can see that this traffic is going this way, this traffic is going other direction, and so on. It's very nice, colorful visualization of the optical flow. So this is another crowded sequence. Again, we are showing these optical flow for different objects in cars like that. So now there are lots of applications. So this is again a basic building block of computer vision for the analyzing video, analyzing sequences. As you saw in the single image, is a basic operation is finding a gradient, direction, gradient, magnitude. We have been using this again and again. Now when you have two images, this will be the basic thing, multiple images. So there are lots of applications. You can do the segmentation. Suppose if you have video, you want to say which objects are moving, which are not moving. So compute optical flow, and you can say, well, this optical flow is significant, so it must be moving. If there's optical flow very small, it's not moving. It's a pretty simple idea. And of course, as we have talked about, you can recover the 3D from the sequence of images. It's called structure for motion. So this will be input to structure for motion methods. And another good application of this optical flow is that you can come up with the global alignment of the video. Say you get a video from a UAV, unmanned aerial vehicles moving, and there are objects moving, there are car moving, people moving. So there are two motions. One is a motion of the camera and the motion of objects. Or if you have camcorder, it's shaking, and then you're recording the video. So what you need to do is stabilize the camcorder so that it doesn't have the global motion. Then you can see the video. So some of these camcorders actually, they have the stabilization built in. So even you shake, the video won't shake. So we are going to talk about how you can write a program which will do that, and that the input will be something like optical flow. Okay, so of course, optical flow is used in compression. MPEG, which does the motion compression. That is the idea there, that you compute the difference between this frame and that frame, and that difference is computed by optical flow, that this pixel, how much it moved compared to this frame. So if these frames remain the same, there's just motion, then you can synthesize this image from this one, just applying this displacement to each of the pixel, then it will look very similar to this one. And there may be a little difference, and you find a difference and you encode that. So that's the basic idea of the motion compression, the MPEG. And as you know that some of the MPEG encoders are free, you can get encoders. Some of them are very expensive. And that is the idea, that how well you can compute these displacement vectors so that you can get a very good compression. So this optical flow idea was introduced by Horn and Shunk. As we talked about, Berthold Horn is one of the famous researchers in computer vision at MIT. He has also a book called Robot Vision. And Brian Shunk was his PhD student, and they started this formulation of computing the motion between two frames, what they call optical flow. Okay, so the idea is simple. Since we have the video, so we have now three-dimensional function, f, x, y, t. F is a function of three dimension. So far we have been talking about a single image, which is a function of two dimension, x and y, rows and columns. Now we have rows, column, and time, what frame number we have. So what they say, well, let's look at two frames. frame at time t and frame at time t plus dt. So these frames are taken very short time apart. Typically there are 30 frames in a second at many frames. Not many things change. So therefore, if I take a pixel at xy in a frame 1, or the frame which was taken at time t, and I look at a pixel close to this xy in the next frame, the frame which was taken at t plus dt, which is close to that, which means I make small change in x, say dx, small change in y, which is dy, then the intensity at xy in the first frame and intensity at x plus delta x, y plus delta y will be very similar, because there won't be much change because I'm taking quick frames and they're very small. So that is called brightness constancy assumption. Say brightness or intensity is constant in this frame at this location and in this frame at this location, which the location is same with a very small change from x to x plus dx, y to y plus dy. So that is a basic assumption, which is which makes sense. Now what we are going to do, that we'll find a Taylor series of the right side. Again, this is a concept you will see again and again. We have already used this for a couple of times. So we'll find the Taylor series of this, which means we'll come up with an approximation of this in terms of derivative of this function. So the left side will be same f(x, y) of t. The right side will be, we will find that Taylor series at x, y of t. So the value of this function at x, y of t, then derivative of this with respect to x, which is shown here, and then x plus dx minus x, which will become dx, and then derivative of this with respect to y will be df by dy, and then y plus dy minus y, which will become dy, and similarly for t. So this is the Taylor series approximation of the right side using only first order terms. Now as you see that this will cancel with this, so we will get fx dx, so it's just a partial derivative, fy of dy and ft dt. So then what we are going to do is divide this, every term in this, by dt. So this will become dx by dt, dy by dt, and dt by dt. So dt by dt will become 1, so it will become ft. And dx by dt is change in x with respect to time, and dy by dt is change in y with respect to time, which we'll call u and v. And that is essentially optical flow. Okay? So now we have this very famous equation, fxu plus fyv plus ft. And this equation is called optical flow constraint equation, and this again you will see many times. It's used a lot of places. Now if you look at this is equation in a way is the equation of a straight line. The line is in u and v coordinates. So v is given by this, because I bring in this here, I brought the others on this side, so they'll become minus fxu minus ft, and then divide by fy, which is shown here. So this is the equation of a straight line in u and v space. Okay, so we can actually draw that. So this is u and this is v. It's the same thing like x and y. Instead of that we'll have uv. So if I put the u is equal to 0 here, then v is become minus ft upon fy, okay, which is shown here. Similarly, if I put v is equal to 0, then I can find the u's value, which will become minus ft upon fx. Okay, so I have 2 points, then I can draw the line between them, so which is shown here. So now as you can see that this is a one equation and it has 2 unknowns. The unknowns are u and v, and we know how to compute the fx, fy, ft, which are the derivatives, and there's a mask for that, and we have been talking about that, and I will show you again. So therefore at each pixel we can compute fx, fy, ft, but now we have one equation, 2 unknowns, So that's a problem. Okay, so now what we can do, let's say the optical flow, the true optical flow was U star V star. This equation of a straight line tells you that we don't know precisely what is the optical flow because it's under constraint. We have one equation, two unknowns, but it tells you the optical flow will lie on this line because this equation satisfies the line. The way we got this line was using this equation. So it can be this one, this one, this one. It can be anywhere on this line, but we don't know. Okay? So let's say somebody told us that it is here. This is a true optical flow. Then we can look at this vector, and this vector we can divide in two parts. One is this call, which is parallel, and this is a normal, which is t. So if you take these two vectors, you get this vector. Okay, that's a vector addition. So what you can show that this vector, which is a normal vector, which is d, can be given by this, because this is a simple trigonometry. You have a triangle here, this you know, and this is d, and you can easily drive this thing, and you can do that at home. So which means that if the true optical flow is this one, then we can easily compute the d using these derivatives at each pixel, but we don't know the p part, which is this one. Okay, now let's say, well, somebody else told us, so that's why d is called normal and p is called parallel flow, but somebody told us no, it wasn't this one, actually it is this one. So again we have this vector, we can divide in two parts. One is this d, and now p will become this much longer. So as you see that the d, which is the normal flow, in both cases is same, and it's given by these derivatives, but the p changes, and that's what we want to estimate. So that is the basic. Now what Horn and Shunk did is look at formulate this as the optimization problem. You say, well, this is under constraint system, we cannot compute the optical flow for every pixel using one equation for each pixel. So we are going to formulate this as optimization problem. We are going to say, well, we are going to compute UV at every pixel, which has to satisfy, of course, brightness constancy, this optical flow constant equation, which we just derived. Which means that if the optical flow at a given pixel, this is double integral, which means we are going to do this for every pixel. So if the optical flow is correct, then this ideally will be 0. Okay, but it may not be exactly correct. It may be small error. So we square the error and be small number. Other thing we want to do is we want to say second constraint. We want to put in that optical flow which we compute, it will be smooth. It has to be smooth. So that helps us to actually formulate this way so that we can compute, because if you just use the optical flow constraint equation, we don't have enough constraint because one equation, two unknown. So this helps us and makes sense that the optical flow mostly will smooth, that if the object is moving, all the pixels in the object will have similar motion, except the boundary will be a problem, as I showed you in that garden sequence of the tree. So now we have two constraints, the brightness constancy constraint or optical flow constraint, and then smoothness constraint. And smoothness constraint, the way we are going to do it, we say the optical flow UV is smooth if we find the derivative of u with respect to x and derivative of u with respect to y. Similar derivative of v with respect to x and derivative of v with respect to y. If you square them, it will be small. Smooth means not much change. So when you find a change, square that should be small. So that's why we want to minimize these both things. Ideally, this term will be 0, and this should be very small. There will be some error, and this also should be very small. So now I'm going to jump here, and I won't cover the how to take this integral, double integral, and minimize that. This is something called variational calculus. So it is similar to regular calculus. As you know, the regular calculus, you have function, you can differentiate it and equal to 0, and then you can find the minimum maximum. So when you have this, is actually, instead of function, is a functional. It's a function of a function. And so for that, and this involving integral, so it's another calculus called variational calculus. But the basic idea is very similar to regular calculus. So we have this function we want to minimize, so we are going to differentiate this. I'm going to tell you, approximate idea. It's not exactly right, but just to give you intuition. So as you see, well, if you differentiate with respect to u, you get one equation. You differentiate this with respect to v, you get another equation. You have two equations now. Whereas u, v are the variables. So now, as you know, that when you differentiate this with respect to u, so this is first square, so you get 2 here, then you get this thing, and then you differentiate this within u. So this has only u, so it will become fx here. And this doesn't have u, so you don't get any term here. Similarly, if you differentiate with respect to v, you will get this thing there with 2, but then since it's equal to 0, so 2 can be got rid of, and then differentiate with respect to v, so we'll get fy. That's what we have. And then we have second term. Now this is second derivative, the first derivative with respect to x and y and so on. We'll differentiate this one, what we are going to get a Laplacian of u, and for the second one we are going to get Laplacian of v. Okay, so Laplacian, as you know, we have talked about Laplacian Gaussian. So Laplacian of u will be second derivative u with respect to x plus second derivative u with respect to y. Similarly, Laplacian of v will be second derivative of v with respect to x plus second derivative of v with respect to y. So we'll get these two equations, and so this is a Laplacian, as I just told you. So so this tells you how you compute these derivative applying these masks. So we have looked at the different versions of these masks, and these are particular masks which are from Roberts, another researcher which came up with this, and these are a little different. So if you want to find the first derivative in x direction, we are going to find a difference like this, which you have talked about, on the left difference. But here we are going to have one more on the top, so kind of average out. So as we have done before, we are going 3, but this guy just said let's do 2. And now since we have 2 images, we are going to compute the first derivative in the first image with respect to x, and first derivative with respect to x in the second image, sum it up, and that will kind of average out over 2 images. See, if you just apply this one, it's averaging out in the one image. So you get an estimate from this, and you divide by 2. It gives you the better estimate of first derivative with respect to x in that image. And otherwise we can have just use this one, simple, just this one. But as we have discussed before, it's better to look at several, one above, one below, and so on, to give us a better estimate. So it's averaging out. Now since we have 2 images, it's averaging extended to second image. So we're going to apply same mass, the first image and the second image, we'll get this estimate and give fx. And the same way we'll do the fy, we'll just rotate these mass. Now the difference will be in this direction, like that. And then ft is in temporal direction. So we'll apply this to the first image and subtract, temporally the same pixel. Okay, so these are the masks which can be used to compute fx, fy, ft given 2 images. And that's what this is. So then the Laplacian mask is like this, that if you want to compute the second derivative x and second derivative y, add them up, so you can apply a mask like this directly. So these weights are different. So you left and right have 1/4 and top and bottom has 1/4, and then these are zeros. So if you look at this carefully, that that what we are doing here is the discrete version of this Laplacian will be that we take the average of the 4 neighbors. That's why we have 1, 4, 1, 4. So find the average of 4 neighbors and subtract from the central one. Okay, this is minus sign and this is plus sign. So the approximation of the Laplacian is like that, and that's essentially we are going to use. So discrete version of this Laplacian will be the average subtracted from the central pixel of u, and similarly for v, the value of v at the central pixel where we want to compute, and subtract from the average, and that's a Laplacian approximation as I showed you in the mask. Okay, so now even though this was a differential equation, we reduce it, we discretize it. Now we have in terms of these things which we can write a program to do it. So now we have these 2 equations. So we know everything. We know we can compute fx, fy, ft at every pixel. uv is unknown. That's where we compute. And u average is for a given pixel. We look at left neighbor, right neighbor, top and bottom. Sum them up, divide by 4. That's u average. And then u is what we want to compute. Okay. So now 2 equations, 2 unknowns in u and v. We can solve these. You can solve these 2 equations. Pretty simple, linear equations. And you can do this at home, and you'll find out that u is given by this, v is given by this, where p is this one and d is this one. Those are in terms of derivatives, fx, fy, ft. Okay, so what we are going to do, what they did, Horn and Chung proposed, say, well, let's do this in an iterative fashion. So we don't know optical flow. So we're going to initialize optical flow to say 0. So we'll have 2 arrays because we have a vector at each pixel. So corresponding to the, given 2 images, we'll compute 2 arrays. One will be a U array, other will be a V array. And once we are done, then we'll have optical flow, 2 numbers at every pixel. So we'll initialize, so the UK and VK, yeah.
In the previous slide, when we needed to, so we have the U minus U average, and we said the U average is the average of the...
Four neighbors.
For the neighbors. However, we do not have the U, so how we...
That's right, that's a very good question. So that's what we are going to explain here, that's why we need iterations. So in the beginning, since we don't know UV, we're going to assume all zeros. Initial estimate of U will be 0. But so there'll be U0, V0. That iteration number will be with K, UK, VK. So you start with U0, V0, all pixel 0. Then from there we'll compute U1, V1. From U1, V1 we'll compute U2, V2. So we'll do the iteration, and that's what is going to happen. K is equal to 0 and initialize, and then we'll repeat, we'll use these equations and where these are in, and keep doing that until we converge, and that's it. So this algorithm is actually very simple, 2 lines of MATLAB code. You can do it at home after the class. So these are the typical images we used to use in the old days because it was very difficult to get real images. So these are synthetic images. What is happening here, there's a square in the middle which is moving 1 pixel to the right. And these are called also random dot because the background is randomly black and white, these pixels, and also the foreground is randomly black and white. But the contrast between the background and foreground is different, so that's why this appears whiter than this. So you generate this and you superimpose this object, then you do the same thing, but you move this by 1 pixel to the right. And so this will be input to your Horn and shunt. If you do that, you run through that, the first iteration you will get like that. So as you see, some of these arrows start appear. After 10 iteration, you will get these. And that's the optical flow, because you know that how much displacement you did from first frame to second frame. So that's a pretty simple algorithm computing the optical flow using Horn and shunt. Okay? Any question on this? Okay, so now this of course was more than 30 years ago, 1980s. Since then there are many methods have been proposed. There are maybe 10,000 different papers talk about optical flow, because optical flow is so essential, so important to compute accurately and quickly. Is basic operation. Lots of vision algorithms are based on optical flow. What has become very popular is actually a very simple method, and this was proposed very close to Horn and shunt, a few years after or before, I think. This was by Lucas and Kanade from CMU. Takeo Kanade is a very famous researcher in computer vision. He's in Carnegie Mellon, and Lucas was his student. And so this is a very intuitive and very simple method, and it actually works pretty good. So the results I showed you earlier were from there. So if you look at this optical flow equation, as we've been talking about, so one equation, two unknowns. At each pixel we can compute fx, fy, ft, and we have to compute uv. So one equation, two unknowns, we have a problem. Now how about we say for a pixel we look at a small neighborhood around pixel, say 3 by 3 neighborhood, and let's assume the optical flow on these all 9 pixels is the same, because again smoothness assumption, optical flow should be very similar in all these pixels. So which means that every pixel in the 3 by 3 neighborhood will give one equation. Okay, so we'll get 9 equations like that. Of course, at every pixel, fx, fy, ft will be different. We're going to apply these masks. So we have 9 equations, 2 unknowns. So this is called over-constrained system, and which means we can solve this. Okay, and so if you do that, we can put this in a matrix form. So we have uv, which are unknown, and ft1 to ft9 is in here. And then from this we'll get fx1, fy1 in the first pixel. So multiply this, fx1u plus fy1v is equal to minus ft in the first equation. Multiply with the last one, you get this equation, and so on. So this is a very matrix form of these 9 equations. So the matrix we have has 9 rows and 2 columns, and the vector on the right side has 9 rows and 1 column. So this is 9 by 2, 2 by 1, and this is 9 by 1. So now, and we will call this as a matrix A for the short form, U as a vector U, and FT, these are bold, is a vector. Now see the simple way you have learned these matrices, a linear algebra course, that we can invert, we can bring the A on the other side, then we can find U, and it's that's what we want. But the problem is that A is not a square matrix, so we cannot invert it. It is a 9 by 2. A square matrix means number of rows, number of columns same. So what we do in that case is we force it to be a square matrix. So what we are going to do is we'll multiply on both sides on the A transpose on the left side, A transpose on the right side. That's what we have here. Okay, so now this A transpose A is a square matrix because A was 9 by 2. A transpose means take the rows, make columns into rows. So if the A is 9 by 2, A transpose will be what? 2 by 9. So we have a 2 by 9, 9 by 2, so this will become 2 by 2. Okay, so we can actually invert that. So then this bring in here, so U will become this. We already have A transpose and F. So this we know, these we know, then we can compute U. Okay, it's very simple. It's optical flow, you can compute like that. So this thing is called pseudo-inverse. This whole thing is called pseudo-inverse. It's not really inverse, because if you have 2 by 2 matrix we can find an inverse, but this was 9 by 2, so we multiply A transpose both sides, we bring it there. This whole thing is called pseudo-inverse. Okay, so and this also again the concept we are going to use many times. A very simple concept and very useful concept. So now another way actually to get the same result is to look at this function. So see, we have 9 equations, and we say we want to estimate UV such that these 9 equations are satisfied. Satisfied means if the UV is exactly correct, then every equation will become 0. So right, that's the equation. So then, but UV will estimate, it won't be exact. So it'll be a maybe, when you add it up, it may be small positive number in some cases, it may be small negative number in other cases, and so on. So we'll have errors. Ideally the error will be 0, but there may be errors. So now what we do, we take the errors for all the 9 pixels, we square the error for first pixel, square for second pixel, third pixel, we add them up. So we want to say that, well, we want to estimate this UV such that this square error is minimized. Okay, and this process actually is called least square fit. It's a very popular method to find the parameters, in this case UV, by minimizing the square error. Minimizing means least, that's called least square error. That's what we have. Okay, so we have now function. This function is of UV, and we want to minimize that. Now whenever you have function of, you want to minimize, what you do? If you have function you want to minimize, what's the calculus operation you do? You differentiate. Okay, so we have 2 variables, U and V. So we're going to differentiate with U equal to 0, differentiate V with respect to equal to 0, and that will give us the 2 equations. We can find UV. So if you differentiate this with respect to U, so this is a whole square. So if you differentiate x squared with x, it will become 2x. Then you differentiate the within it, which is this term. So that's what you will get. This will become 2 and this whole thing. Then you differentiate this with respect to x, will become fx, which is here. This does not have u, this does not have u, and this will be first. Differentiate this with respect to v. Again, this will become like here twice, but we can get it off twice because on the other side is 0. And this thing repeat, and then differentiate it with respect to v, become fy. So we have now 2 equations and 2 unknowns, and this is through the minimization approach. Earlier we did a matrix thing. We put matrix and we just inverted and so on, but they're exactly the same. So then we can take these and again multiply these because this is summation. Remember, we have 9 equations, we are doing this 9 times. So we can break this up. We can say this multiply with fx, this term, which becomes here, this is another term, summation, this become another term, and we can bring this on the right side, become negative. And similarly we can multiply fy here, this will become fx, and fy u, this will become fy square v, and then this multiply with this, and it will become fy ft on the other side. So we have these summations, and still we have 2 equations. And we can write down this in a 2 by 2 matrix because we have 2 equations, 2 unknowns. So UV is what we want to compute. This we will apply mass, we can compute, and these terms will also be computed. So if you multiply UV with this first row, you'll get first equation. If you apply this with second row, you'll get second equation. Same way as we did before. So now this is a 2 by 2 matrix, and we can invert that. Okay. Earlier we had 9 by 2, and we were not able to invert, but this is 2 by 2. We can invert that. And 2 by 2 inversion is pretty easy. As you know, find a determinant and just do this and that, and this will become inverse. This is a determinant and this is inverse of this 2 by 2 matrix. And this we have the same thing. So now we have actually the solution for UV. So U will become this multiplied with first row divided by this, and V will become this column multiplied by second row divided by this, and that's what we have. So we have actually just two lines, UV in terms of the derivatives of the images fx, fy, ft. So that's again a very simple MATLAB code. You can just type this up, you'll have optical flow. You take two images, compute fx, fy, ft every pixel, do this thing, and this is summation that's for 9 pixels. For every pixel, these summations are 9 pixels. Okay? And that's it. So that is the Lucas-Canade optical flow algorithm. Very simple, and actually it works pretty well. So these are the results you will get. Now, one thing you will see that that some places the optical flow is not correct because there's a large motion, and that's why we will need what is called pyramid. Now this is the same thing. You'll get some rough estimate of this optical flow. The places where there's large optical flow, this method will not be able to compute. The reason is because when we are computing, this whole thing depends on derivatives. We are computing derivatives that are small 2 by 2 masks. But if the motion is, say, 15 pixels, and the 2 by 2 mask will not be able to make a distinction between 15 pixels or 2 pixels because you're looking at a very small neighborhood. So we're going to talk about how to change this using pyramids so that we can apply the same Lucas-Canade, which give you much better results, which is shown here. Okay? So these, in summary, both method, Horn and Shunk, and the Lucas-Canade, they are for small motion. Now, if the object moves faster, the brightness changes rapidly, so the small masks for computing derivative will not be enough. So that's why we are going to build a pyramid which will take the large motion, reduce the motion. Suppose if the original resolution we have 16 pixel motion at a given pixel. We may reduce the image from 256 by 256 to 128 by 128. If 256 by 256, its motion was 16, when you reduce half in x and y, it will become 8. When you reduce further, it will become 4. Further, it will become 2 and 1. So this pyramid, again, the scaling thing we are talking about. So similarly, idea here that the large motion can be reduced using the pyramid, and then when it's a small motion, then we can apply this method. So the notion of pyramid is very useful for estimating the correct motion, correct optical flow, and also it is useful for dealing with scale, as we talked about in human detection. Okay? So then you will get something like that. Now this is the tree sequence, and the optical flow is pretty good using the Lucas-Canade with pyramid. And this is another sequence also it's pretty good. So that finishes the optical flow. So do you have any questions? Since we don't have much time, I don't want to start the next thing. Yes?
The U and V were the vectors, correct?
U and V together is a vector. U is a scalar, V is a scalar. So U tells you displacement in x direction, and V tells you displacement in y direction.
Those came from the dx and dy from the original.
Yeah, dx by dt is U, dy by dt is V. You know? So change in x with respect to time is U, change in y with respect to time is V. Yeah.
Which are the applications of optical flow?
Yeah, as I went through this before, so there are many applications, and the one is the segmentation. That one of the operation is that we can segment, we can distinguish the objects which are moving, which are not moving. You know, so if I have camera, most person are sitting here, but some person get up and moving. So I'm interested what is moving. So since I will have estimate of every pixel, what's the motion. So the stationary pixel will be zero motion. There's no motion. So I can use optical flow for segmenting. Say, well, this person is moving, this person, the rest people are not moving. So it's very important application. One. The second one is that we can recover the 3D information, which is called structure for motion, that I can estimate how the camera is moving or people are moving in 3D, and also their shape in 3D. You know, as compared to, because I have 2D sequence of 2D images, so I don't know 3D. I can find this person is closer to me than Oliver. So that's a depth perception, the 3D information, and that's what humans also use motion to estimate 3D. In addition to stereo, lots of other cues. So the basic input to these methods are optical flow and the motion correspondences. And then I told you that you can take a video, say, obtained from UAV, where it's moving, and you want to get rid of this global motion, stabilize the video. And because see, if you have UAV is moving, the cars are moving, people are moving, so there are lots of motions. So due to UAV moving, every pixel move. So we want to stabilize, move the global motion, then look at the object's motion, and we can use optical flow for that. And we'll talk about a method. We will also implement a method to align the frames, move the global motion. So, and as I told you, that some of these camcorders, you buy, when you record a video, some people have tendency they will shake the camcorder. But if some of these good ones, they have a stabilization, that they will stabilize it, the video won't show the motion. That's what they do actually. And also, in order to compress video movie, you use the optical flow, the displacement, because the difference, the movie consists of sequence of frames, and when you look at the frame 1 compared to frame 2, most of it is same. The things don't change that much. So maybe it moves a little bit. So if you can find these motion vectors, optical flow, then you can just send that, and then you can reproduce at the uncompression level. And so there are many applications of optical flow. That's why it's a basic operation. So it gives you how much is a movement in the image plane.
What is the difference between why are some MPEG for decoders much more expensive than other ones?
Yeah, so I think the reason is that if you can estimate the motion very, very well, very accurately, then, and you can compress a lot, say if you have a 1 hour video, and if you have really in high definition video, if you have a very efficient method to compress it very, very small, so that we can transmit very quickly, and you can get online through your cable modem and so on. So the quality of video after the uncompressing, and the size of the video is small, then you need a very, very efficient algorithm, and these are proprietary algorithms by different companies. They are implemented in hardware, they are specialized and so on. So that's why some of these are very expensive as compared to some other one. Any other question? No question. So then I'll see you on Thursday, and please show up for the session tomorrow with Burkan if you have any questions on MATLAB and so on. So you want to make sure that you feel very comfortable with MATLAB, because the next assignment will be pretty involved on the SIFT. Okay, thank you.